Good morning, everyone. In the previous lecture session, we had seen example 5.13. In that, we had seen how to write register transfer statements for memory reference instructions which were given to us additional to the ones explained in the textbook. Now, in today's session, we'll try to solve one more example. Here, in this example, we are asked to give the sequence of computer instructions needed to execute the following operations in the basic computer. Now, look over here. We are asked to write computer instructions and not register transfer statements. Okay, so what do you mean by computer instructions over here? We have studied 25 computer instructions for basic computer. We have to use those 25. Out of those 25 instructions, we can use any instructions to perform the following two operations. Is that clear? The 25 instructions which we had seen were memory reference instructions, register reference instructions, IO instructions. So from all those 25 instructions, we are free to use any of the instructions from the basic computer to perform OR and EXOR operation. Okay, similarly, you may be given any operation to perform and you will be able to do that. Assume that the required operands are available in the memory. So suppose you are asked to carry out A or B. Okay, this is OR over here, logical OR. So if you are asked to do A or B, it has been said that you have to assume that the required operands are available in memory. So this A is somewhere over here, B is somewhere over here at location X, at location Y. Okay, so in your memory, you have the operands A and B. And the final result of the operation is to be stored in memory word. So you may store your final result somewhere in memory word here. Okay, you have to finally, after performing the entire operation, store the final result in the memory word. Also compute the total time needed to execute the given operation. So we also need to calculate the total timing signals that are required to perform this particular operation. See, the question is very easy. Now let us see how to do it. Now suppose I want to do A plus B. We know that in our basic computer instructions, we have an instruction and we have instruction complement. Okay, using these two, can we perform A plus B? Can I write A plus B as A dash dot B dash whole dash, De Morgan's law? Okay, now A dash can be done using CMA instruction. B dash can be done using that. This is my AND operation and again I'll be complementing it. So using these two operations, I'll be able to perform A plus B. Okay, so now let us write the sequence of operations required. First of all, I'll have to load A into my accumulator. Then only I'll be able to perform A dash. And we know that the operands are available in the memory. Okay, so first instruction that I'll do is like I'll write LDA, suppose from location X. So I'll have A in my accumulator now. After LDA, what is the next thing that I need to do? Complement accumulator. So after I perform complement A, I'll have A dash in my answer. Okay, now next what I'll have to do? I'll have to store A dash somewhere. Why? Because now I need to complement B. For complementing B, I need to first bring B to my accumulator. But accumulator has A dash, so I'll have to store this somewhere. So what I'll do is, I'll perform the STA operation and I'll specify some location, let it be location P. So at location P in your memory, you will have A dash stored. After that, now I'll bring B to the memory. LDA, B is at location Y. So I'll have B in my accumulator. Again, what will we do? Complement, so I'll have B dash. Now what does your accumulator have? B dash. I want A dash dot B dash. So what I'll do is, I'll simply AND it with location P. PK under I have A dash, right? So what I'll do is, I'll simply perform the AND operation. Are you all getting me? First, we loaded A to accumulator, we complemented it, we stored it in memory, then we loaded B, then we complemented B. Now accumulator already has B dash. So when I perform AND with some location, what would happen? Whatever location I have specified, from that location it will take the operand and it will it will perform the operation with the operand that is already available in B dash. So and will give me A dash dot B dash. Now what I need to do? I again need to perform complement. Why? Because I want this thing. Okay. So A dash dot B dash is available in my accumulator. So what I'll do is CMA. Again complement. So this will give me A dash dot B dash whole dash, which is same as A plus B. Now A plus B is there in my accumulator. Finally, what was told to us? Store the answer of the operation to memory. So what would be the last step? STA. Okay, I'll specify Z. So at location Z, you will be having A plus B in memory. Was it easy? So these are the sequence of instructions which I'll be writing for performing the OR operation. Load, complement, store, load, complement and store. Done? So first part of the question is done. Now we are also asked that how many timing signals would be required in all. We know that load is a memory reference instruction. Okay, so memory reference instruction 0, 1, 2 is fixed. 0, 1 for fetch, 2 for decode, 3 for fetching effective address, and my instruction will start from timing signal T4. So total, how many instructions, how many timing signals LDA required? 6. You recall T0 to T5. Recall the RTL statements which were written for load. The last one was T5. So total 6 timing signals are required for LDA. Similarly, CMA is a register reference instruction. It requires 4 timing signals. STA, T4. Okay. T0, T1, T2, T3 are fixed, and only in T4 it will be completed. STA, store accumulator. So AC to M of AR, right? Then LDA again, 6 timing signals, CMA 4 and 6, CMA 4, STA 5. Okay, now just make a total of these. How many timing signals required? Total 6 plus 4, 10, 20, 30, 40. So what would be my answer? Total 40 clock cycles are required to perform the OR operation. Was it easy? Okay, let us try one more. Okay, now you'll be able to do it on your own. EXOR. We are asked to perform EXOR. EXOR operation, we know that we write EXOR operation like this. XY dash plus X dash Y. Now we do not have plus instruction. So how will we do? Again, the same way that we performed OR over here. So this is OR, okay? So here how will we write? XY dash whole dash into, sorry, this dot operator again, X dash Y complement. This is A plus B. Okay, what we are doing is nothing, A dash. So this is A dash. This is B dash. A dash dot B dash whole dash. Okay, so whole dash. So we need to perform this much. And now we can write the set of instructions, computer instructions for performing this thing. Let us quickly start. First of all, load LDA. So we will load Y, this one. Then we will complement it. Okay, so we'll get Y dash. After that, what I need to do is load it with memory location of X. Sorry, AND it with memory location of X. So AND. Once I perform AND, I'll have XY dash. Okay, this much is done. Now what I need to do? Again, complement. So I'll get XY dash whole dash. This much clear? Now this part is done. So what will I have to do? Store it to memory. STA. Okay, this will be stored in memory at location whichever is specified. After that, again load. What we will load? This one, X. Same thing repeat. After X, complement, CMA will give me X dash. Then what we need to do? Perform and end with what? And with Y. So you will get X dash Y. X dash is already an accumulator. When you simply write and, it will AND it with Y. Now again, what we need to do? Take complement of X dash Y. Okay. So what we'll write? CMA. Now we have X dash Y whole dash in our accumulator. So what I need to do? I need to perform AND operation only with the value which we had stored somewhere in memory. So I'll simply write and provide the location. So what will it give me? X dash y whole dash into, this was already an accumulator, and this thing was stored in some memory location. So you will be ANDing it with this. So this thing done, this dot this. Now what is the last step to do? Complement again. Okay, so this will give me the final result. Understood? This is nothing but x dash y plus xy dash, and which is nothing but x XOR y. Fine? So this is the result in accumulator. Again, we have to store the final answer in memory. So what would be the last step? STA, store to memory. Are the steps clear? Okay, now let us quickly count the timing signals. Load 6, complement 4. All register reference instruction by default takes 4. Okay, and again 6, complement 4. Store 5, load 6, complement 4, and 6, complement 4, and 6, complement 4, and store 5. Shall I quickly add it? 10, 20, 30, 40, 50, and 60. So if I want to perform XOR operations, I will need total 60 clock cycles. Understood? So this is how you may be given any operation to perform. You have to recall the different instructions that we already studied, use those instructions, perform it in particular sequence, and then you'll be able to perform any given operation. You may be asked to perform NOR operation. So all you have to do is A plus B whole dash. What is A plus B whole dash? A dash dot B dash. So this is very simple to do. Okay, you first load A, complement it, then store it. After that, load B, complement it, and then AND it. So that's done. So this is NOR operation. Okay, see, students generally make a mistake. They first perform A plus B using the previous example that we did, and then they take its complement. In this case, the number of steps would increase. But instead of doing that, simply perform this A dash dot B dash. A plus B whole dash is A dash plus B dash. So when you perform this, number of steps would decrease instead of increasing. Okay, so this is how we'll be performing any operation given to us. Calculate the total timing signals required, and this is how this type of question can be solved. These types of questions are asked in previous year question papers. Okay, but they are very easy to implement if you have understood the logic. So if you have any questions, you can ask me regarding these types of questions. In the next class, we'll be solving examples based on control logic.